All right, section 3.3, and this is sort of part B, if you will. We're going to take a look at division of whole numbers today. And the first thing we're going to start with, just like we did with multiplication, is a definition of what it means. So division of whole numbers is if we have any whole numbers A and B, we have some conditions. One of the conditions is that B cannot be 0. Then A divided by B equals C if and only if C is the unique whole number such that A equals B times C, or B times C equals A. Is there something written wrong? Yeah, my pen's not very clear. We'll fix it and make it more readable. B is not 0. Why can B not be 0? You can't divide by 0. And the reason you can't divide by 0 is, what if B were 0 under this definition down here at this point? What would happen? Yeah, we'd have B equal to 0, so 0 times C would still be 0, and A would be 0, and everything would be 0, and all of a sudden we've got a problem. So it's because of the way we define division that this cannot work. A is called the dividend. B is called the divisor. And C is called the quotient. So the number we're dividing is called the dividend. The number we divide by is called the divisor. And then the result of all of that is called a quotient. And if you'll remember, for a section in chapter 1 or chapter 2, we talked about the symbols for the different number systems, and we used a Q to represent the rational numbers, Q for quotient. This is where the Q comes from. All right, so we have several models for division. We're going to start with the set model for division, and there are two set models for division, and one of them is a partition model, and then there's a variation on that. So I'll show you the difference between the two because it comes up much more prevalently when you get to Math 2, and it's important to recognize that there's two ways to describe it. All right, so to start with, Abby has 24 rocks. We've done this part before, haven't we? But we had Eli steal them last time, I think. All right, so 24 rocks. She wants to give them to 6 of her friends. How many rocks will each friend get? So to start with, you're going to draw your 24 rocks. I'm just going to do a circle. So I'm going to say that the rocks are all different sizes because then that justifies why they look weird. How's that? The rocks are different sizes, actually, so that's all right. She wants to give them to 6 of her friends. So what would we have to do in order to make this work out well? We need to put them into 6 groups, don't we? So somehow we need to take what the image is here and we need to divide it evenly into 6 different groupings, right? So this would be a description of what happens in your classrooms when your teachers have you number off into groups. They decide in advance they want 6 groups, and so you number off by 6s. And then the 1s go to that corner, and the 2s go to this corner, and the 3s meet in the middle, and so forth. That is this kind of a model. Now, unfortunately, the way that I drew my picture doesn't lend itself very well to that, does it? So I'm going to move some of these objects around in theory. We'll see if it really works. Maybe not. All right. My whole screen's moving. It's not what I want. Okay, if I move them into 6 groups, this is a little bit better at least. I can split them up like this. Did I not get 24 rocks? Apparently I'm not. Oh, maybe I did accidentally delete one. All right. Well, we'll add me an additional rock apparently. Heaven's sake. Nothing's going quite right today. There we go. We'll split it like that. All right, so I have 6 groupings, right? And each of the groupings, each friend gets how many rocks? 4 rocks. So there's 4 rocks in each group. Okay. So we've decided in advance how many groups we want to split these rocks into. That's what this model or this variation of the partition model does. Okay? The other model is different. So again, Abby has 24 rocks. She bags them together in groups of 6. She gives the bag to each friend. How many friends get a bag of rocks? What's different in this model?
They start off with more rocks.
Okay.
Like they're going to get.
Okay, so whoever gets the rocks is going to get more. What else is different about this model?
When you say how many rocks, which one is
Instead of
asking
how many friends? Okay, so in this case, we actually have decided the rocks are going to be in groups of a certain size instead of splitting them into a certain number of groups of rocks. Does that make sense? This one, actually, my model draws easier. So okay, so in this model, what I'm actually doing is I'm bagging the rocks up into groups of a certain size. So there are 6 rocks in each group. So I group them together in 6 in a bag. And in the end, I get how many bags of rocks? 4 bags of rocks. So how many friends get rocks? 4 friends get a bag. So I had mentioned this in the other problem before, that one of the ways of doing groups is deciding that I want 6 groups and you guys all number off by 6s. That's not how I do groups. I decide in advance how many per group I want, and then I split you guys up. So I say to myself, oh, but I want 2 students per group, or recently I've done 3 students per group. And then I decide and I look at the end and I say, oh, well, that ends up meaning that I'm going to have X number of groups at the end. So I'm trying to control how many people are in each group, not how many groups I have. And that's a very different perspective of forming groupings of things. But they're both partitioning something down into smaller groups. All right. Another model is the missing factor model. This is kind of like the missing add-ins model for subtraction. Okay, we're still working with our 24 rocks. Abby has 24 rocks and she wants to give them to 6 of her friends. How many rocks will each friend get? Okay, so I'm going to do this a little bit differently in the description where I'm looking at the missing factors. So when I'm doing a missing factors model with the same description, right, this problem was the same description, this is the idea of taking this like an equation setup and dividing by this. Another way is you could not have a little square there, you could put a question mark there. Sometimes you'll see some resources do that where there's a question mark. And again, this is an operation of that equal sign, kind of like the problem that we talked about on the board. Equals doesn't mean what's the answer, because the answer is going to be what's in the blank. So we can think about this in terms of a multiplication problem. You could change this, and students will often do this. We would say, okay, well, that's the equivalent of saying 24 equals 6 times what value? Because that's where we start with. We usually start using multiplication tables, not division tables, right? So if we think about this, we say, well, 6 times what equals 24? Then the answer, of course, is 4. So my value here is that they get 4 rocks each. But this doesn't do it from a concrete model perspective, right? It does it from a missing factor perspective. Sort of a back to your multiplication tables or back to flashcards kind of perspective on the problem. Okay, and there's one more model. The other model is repeated subtraction, and you see we've got the same question again, but we're going to look at it from a different perspective. So this one says Abby has 24 rocks, and she wants to give them to 6 of her friends. How many rocks will each friend get? Well, from a repeated subtractions perspective, what we can do is we can take our 24 rocks, and physically what we would do is we would give each friend a rock. And once we give each friend a rock, how many rocks have we given away? 6, because we had 6 friends. So I started with 24 rocks. I gave away 1 to each of my friends. So this is my each friend. Gets 1. Then I have 6 fewer than I started with. So how many rocks do I now have? 18. And then I do it again. I say, okay, great, everybody got 1 rock, but I've got some more left over, so we're going to do it again. So you can almost imagine her going down the line and saying, you pick one. Do you guys ever do this with kids? Right? This is the classic dodgeball pick a team thing going on, right? So we each go back and forth, so there's sort of some fairness involved. So we're subtracting off, in this case, 6 every time because there are 6 teams, quote unquote, or there are 6 groups or 6 friends in this case. So I take away another 6, and how many did I get? 12. I'll do it again, take away another 6, and what do I get? 6. And I take away another 6, and what do I get? 0. Now the answer to the question is not 0, because 0 is actually the result of giving away all the rocks. I know it's going to be 0 because we're working with whole number division, so it's going to be a whole number when I'm done. But what the answer is how many times I gave each friend a rock. That is, how many times did I subtract 6? And I did it how many times? 4 times. So the friends got to choose a rock at 4 different times. Of course, the last person that was choosing didn't really get a choice, but they each got 4 rocks when they were done. So the answer is 4 rocks. The answer to all the questions was either 4 or 6, depending on how the question was asked. Were they all 4s? The way I asked them, were they some of them 6s? 4. They were all 4s, weren't they? Some of them were 4 rocks and some of them were 4 friends. All right, so here's what you're going to do. You guys have done this before, but I'm going to have you do it just with yourself right now. I want you to create a word problem. The word problem should work for almost all of the examples. All right? I had the same word problem for 3 of my 4 examples, didn't I? Abby, the 24 rocks, the 6 friends. And there was one that was different. It was the second one, the variation of that partition model. But you need one example that you can make a variation of to create 4 problems solved in different ways. All right, I know some of you are still working. It's okay. What you should feel like is that the primary difference between these models is not how the problem is started, but how you solve the problem. Does that make sense? How you view the situation that's being described. Just like in the example I gave, the only 2 that were really distinctive, and they weren't distinctive in the answer, of course, but they're distinctive in how you're thinking about it, is the first 2 set models. That is, are you making groups of 6 or are you splitting things up into 6 groups? Those are the only 2 that really are different. The other 2 are very much like the first model I used, where we split things up into groups of 6. Groups of 6 groups. I said it wrong even. I even said it wrong. Into 6 groups. All right. So I don't want to do a whole lot of examples. I just want somebody who is willing to share theirs, one person. Somebody be bold and exciting for us. Bailey, thank you. What do you have?
Ashlyn has 18 dolls. She wants to give them to 6 of her friends. How many dolls would each friend get?
Okay, so this is similar to our rock situation. Now, did you use that same one for the next 2 parts on the next slide, or did you make up separate ones?
Yeah.
You used the same one? Okay.
And then I have to use a different one on the partition.
Okay, so let's do the partition one, the other part of the partition one, so that you can see the difference.
So I said Ashlyn has 18 dolls. She wants to put them together in groups of 3. If she gives one group of dolls to each of her friends.
Okay, so we made groupings of 3 dolls instead of worrying about how many friends we had to split them up evenly. We made groupings of it, and then we're going to decide how many friends get them. Okay, so that's a great example. And then the next 2 parts over here, the missing factor and the subtraction, can be done using the exact same thing. It's just the solution that looks different. Is everybody clear on those? This is a very different sort of a caveat than what we happened when we did the multiplication ones, right? Those actually looked really different, the models did. This is the solutions look different. All right, we have a couple more slides we're going to take a look at. The first one of the last two is the properties slide, deciding which properties hold for division. So closure, does closure hold for division? What are your thoughts? Morgan says no. So Morgan, why not?
Because if it's closed, then it has to be a whole number, right?
When you use, in this case,
Whole number.
whole numbers and what operation?
Division.
Division, because we're doing division on this one, yeah. Can you give me an example where it doesn't work?
Like 1 divided by 5 is going to be 1/5.
Yeah, I'll write it even using the notation we've been doing. 1 divided by 5 is not a whole number. We'll use the notation. This is not an element of the whole numbers, because 1, well, it looks like a 7, but that would actually work too. 1 divided by 5 is not a whole number. And in order to be closed, I have to be able to take 2, in this case, whole numbers, with the operation of division, and I have to be able to get a whole number, and I don't always. I do sometimes, but I don't always. How about commutative property? Does that work? No. Can you give me an example?
Well, just like that one, 5 divided by 1 is 5, but 1 divided by 5 is 1/5.
Sure. The order matters when we divide, doesn't it? Fractions are not equivalent if I have 3 over 5 and 5 over 3. I mean, this doesn't always work, right? Some of them work. What would work? 1 divided by 1. What else? 2 divided by 2. It has to be the same number, right? That's the only way that it would work. How about associative property? Do you notice a theme on the slide? They're all no. They are all no, Hannah. You're exactly right. This one's no, and almost any example you give is going to make it not work, so I'll write down the one that I have because it works out to being whole numbers at least. If I did 12 divided by 4 and then divided by 2, this would not equal 12 divided by 4 divided by 2. And we can work through it to see. You have to do this in parentheses first. So what's 12 divided by 4? 3. And what's 3 divided by 2? Be 3 halves. Over here, I'd start with a 4 divided by 2. What's 4 divided by 2? 2. And then 12 divided by that 2 would be 6. So it would not work. We'd get 3 halves on the left, and we would get 6 on the right. And Hannah's already told us these are all no, so the identity property, why is that one not going to work?
1 divided by 2.
Yeah, it's almost like the same one that we did before up on the commutative property, since we happen to use the number 1 in that case. If we did the division in only one direction, it would work, wouldn't it? Like, I'll use the ones Kristen just used. 2 divided by 1 would be 2, and it would sort of act sort of like a half identity. The problem is that if I do it in the other order, this is not 2, and that's what it has to be in order to be an identity. It has to work in both directions. Do you remember what the 0 property was?
If anything is multiplied by 0.
Yep, so what do you think the identity property would look like in a parallel form to this?
Anything divided by 0.
Yeah. So anything, let's use 2. What happens when I do 2 divided by 0? Is it? Is it? It is undefined. And it's undefined for the very reason that if it had some value, let's say its value, was A, because some of you gave me some answers, then it would have to be true that 0 times A is 2. And that's never going to happen. I don't care what A is, I can't take it and multiply it by 0 and get back to the 2 I started with. So this one doesn't work. Last one, the distributive property actually is a no again, but just like the associate or the identity property, it half works. So I want to show you the direction in which it does work because it's very interesting that it works that way and you probably never thought about it before. So the direction in which it doesn't work is if the division is at front. So let's say I had 20 divided by 5 plus 4. Then if the distributive property worked, it would have to be true that 20 divided by 5, that this is equal to 20 divided by 5 plus 20 divided by 4. What is 20 divided by 5? And what's 20 divided by 4? 5. So this would be 9 on the right, yeah? But what happens on the left? Other way around. We would get 20 divided by 9. And is 20 divided by 9 equal to 9? No, it didn't work. However, it does work if we do it the other direction. So let me erase that last step so I have some space. Let's say that we had 20 plus 10 divided by 5. All right, so what is 20 plus 10? 30. And what's 30 divided by 5? What is it? 6. It is 6. Thank you. So this is 6 on the left, correct? All right, let's try it over here. What's 20 divided by 5? 4. And what's 10 divided by 5? 2. And what's 4 plus 2? 6. It's still 6. It's still not 7, yeah. It's still 6. Okay, so we get 6 on both sides. So this is the one that sort of half works. We saw half of it worked, half of it didn't. So it still doesn't work in general, so the answer is no, but it does work in one direction, which is unusual, because none of the others actually worked hardly at all, right? Just the identity and the distributive property worked halfway. All right, one more example. Sue claims the following is true by the distributive law where A and B are whole numbers. 3 times AB equals 3A times 3B. How would you help her? Okay, so you're going to tell her more about what the distributive law. Okay, so you want to say that the distributive law or property says we'll use the same values that she has, but just change it to addition, or like that, Carrie, that's what you had in mind, right? Yeah. That this would equal 3A plus 3B. So what is it about the distributive law that she's not looking at or that she's not considering? Okay, there's an addition part of the distributive law, right? And what happens in her problem? It's all multiplication. So one of the key issues here, and I'm going to stop writing, but I'm going to let you guys write it down in your own words. One of the key issues about the distributive law is that it's a combination of two operations. Right? It's multiplication and addition operating together. Or multiplication and subtraction. We had one of those too, operating together. The distributive law combines two operations. Her problem only has one operation. What could she do if she wanted to rewrite this in a different way? This wouldn't be right. What could she do to rewrite it? Or what property would she be able to use if she wanted to do something different here? And what property is that, Morgan? The associative property. So if she's wanting to simplify this in some way, or if she had variable values for A and B and she wanted to use them in some way, she could rewrite it like this. That's the only operation she has that she can change the form that's on the left into something else. It's the associative law or associative property. In this particular case, it's not all that helpful, perhaps. You guys would probably like for her to simply ignore the parentheses altogether, wouldn't you? That's because you know a little bit more about algebra than she does at this point, right? So, any questions on this one? All right, go ahead and jot down the homework.